Alright, today we're going to have a look at volumes involving addition and subtraction. So, sometimes when we're revolving things around the x-axis and the y-axis, the volumes that we're trying to figure out are not as straightforward as what we've been doing. So you can see, for example, in this picture here, we've got a line and then a parabola, and we're finding just that shaded region there. To do questions like these, we need to simply just look at the bigger volume and then subtract the smaller volume. So in this example, if I rotate it around the x-axis, all I need to do is find the parabola rotated around, which is a bigger volume, and subtract this straight line rotated around, and then I get the volume of just that curved area. If we look at this line, it has a gradient of minus 4 on 2, which is minus 2, and a y-intercept of 4, which makes it the line y is equal to minus 2x plus 4. So what we're doing here, the volume is equal to pi times by the integral. We're looking at from 0 to 2. Now we can only make it one integral like I'm about to do when the bounds we're integrating by are the same for both the parabola and the straight line. In the next example, it's not the same, I'm pretty sure. Yeah, we're integrating, for example, this one from 3 and then this one from 4, and it's not quite the same, so we can't combine it into one integral. So the integral from 0 to 2 of, again, the formula is y squared. So we're going the big integral first, which is 4 minus x squared minus the integral from 0 to 2 of minus 2x plus 4 squared dx on both of them. Now, since the bounds are the same, we can combine this integral. So pi times the integral from 0 to 2, let's expand all of those things. So we've got 16 minus 8x squared plus x to the power of 4 minus 4x squared plus 16x minus 16 dx. Now if you simplify all that, we've got pi times the integral from 0 to 2 of x to the power of 4 minus 12x squared plus 16x dx. And if we integrate that, we've got pi times by 1 on 5 x to the 5 minus 4x cubed plus 8x squared from 0 to 2. And if you type that all into your calculator, you get 32 at pi on 5. Okay, next one we're rotating about the y-axis. Again, same principle. We're going to rotate the parabola around the y-axis and then subtract the rotation of the straight line around the y-axis. So we're going to, volume is going to be the integral from 0 to 2, not 0 to 2, 0 to, we're integrating up to 4 now. We're integrating up to 4. So the integral from 0 to 4 of these two functions. But the functions are no longer, we're rotating about the y-axis now, so we need to make sure our function is has the subject of x. So our two functions are y is 4 minus x squared, which means x squared is equal to 4 minus y, and y is equal to minus 2x plus 4, which means x is equal to 2 minus y on 2. So we're getting the parabola and then subtracting the volume of the straight line. So 4 minus y squared minus 4 minus y on 2 squared dy. Now if you expand and simplify all of that, you get y minus 1 on 4 y squared dy from 0 to 4 times pi. And if we integrate that, we get pi times by y squared on 2 minus y cubed, 1 on 4 y cubed on 3 from 0 to 4. Substitute all that in, you get 8 pi on 3. Okay, here they start to get a bit fun. How many more have I got? 1 and 2 more. Okay, after this one. So rotating about the x-axis, we've got this funny shape here. Now try and imagine what's happened. You're getting that shape and you're rotating it around the x-axis. So it's going to be like a weird donut shape. It's almost going to be like that track that they do Olympic bike riding on. It's going to be like that type of shape. I forget what it's called. It's not palindrome, I forget. Anyway, it's going to be that funny looking shape, a weird donut thing. But we don't actually know how to find that volume. So what we're going to have to do is, first of all, rotate the parabola around the curve. And we're also then going to have to find the volume of a cylinder, and I'm going to explain that in a second. Now, when we're rotating about the x-axis, our bounds must be in terms of x. So we're thinking, what is this coordinate here? Now, if the equation is y is x squared plus 3, well then that has to be 1 there to make that true. So let's first of all think of what our volume is going to be. Now if you rotate y is equal to 4, so this is the equation y is equal to 4. So that's our first equation, y is equal to 4. We're rotating that about the x-axis, and then we're going to take away this area here, which is the parabola rotated about the x-axis. So the volume, first of all, we need to do, well, the volume is going to be the integral from 0 to 1 of, first of all, y is 4 rotated around. Now the formula is y squared. So now y squared is 4 squared, which is 16, minus, we're taking away the parabola's area, which is x squared plus 3 squared dx. So this is pi times by the integral from 0 to 1 of 16 minus x to the power of 4 plus 6x squared plus 9, which is pi times by 16 minus x to the power of 5 on 5 plus 2x cubed plus 9x from 0 to 1. And if you do that on your calculator, you'll get 24 pi on 5. Now that's one way of doing the question. The other way is realizing that if you rotate this straight line along the x-axis, don't know what I did there, if you rotate this straight line along the x-axis, if you imagine what that shape's going to be, it's actually going to be a cylinder of radius 4 and height 1. Now the volume of a cylinder of radius 4 and height 1 is 16, which is why that 16 comes into there. Now we've got to rotate it about the y-axis. That's much easier there because I'm just getting this shape and I'm rotated along the y-axis. So I'm going to have another bowl looking shape. So we're just integrating the parabola here from 3 to 4. So we're looking at volume being the integral from 3 to 4. Now the equation is y is equal to x squared plus 3, which means x squared is equal to y minus 3. Our formula for rotating about the y-axis is x squared, so we're substituting in y minus 3, which is our x squared dy. So we've got y squared on 2 minus 3y from 3 to 4. If you substitute all of that in, you get pi on 2. That's quite cute, pi on 2. Alright, 2 more questions. Number 3, we're determining the volume of the solid formed when the region bounded by the x-axis, ln of x, and x is e, is rotated about the y-axis. Again, here we're going to draw a picture. So y is ln of x is here. X is e might be here. Now we might know that when x is e, ln of e is 1, so that's going to be a 1 there. And we're rotating it about the y-axis. So going to be a very strange looking shape. We're rotating about the y-axis. That's going to be minus e there. Now we're not after this volume here. We're actually after the volume of this shape. We're looking at this area here, rotated about the y-axis. But the only way we can figure that out is by finding the volume of this whole shape, this like cylinder looking thing, rotated about the x-axis, y-axis, and then minus this smaller area here. So first up, we're looking at rotating. The equation x is e. So this equation right here, that's the equation x is equal to e, that line there. We're rotating that line along the y-axis. So we're looking at the integral from 0 to 1, that's where we're going up by, from 0 to 1 of x squared. Now x squared is e squared, so the integral from 0 to 1 of e squared. Take away, so volume, we've got pi, take away the integral from 0 to 1 of ln of x. Now ln of x is equal to y, and we need to make y the subject of this equation. So y would equal, we need to make x the subject of this equation, because our formula for rotating about the y-axis is x squared equals our function. So x is equal e to the y, which means x squared is e to the 2y. So we're minusing the integral from 0 to 1 of e to the 2y dy. Let's make that one integral. Pi, integral from 0 to 1 of e squared minus e to the 2y dy, which is equal to the integral of e squared. Well, e squared is just a number, so it's e squared y minus, when we integrate e, it's going to be 1 over 2 e to the 2y from 0 to 1, which is equal to pi times by e squared times 1 minus 1 on 2e squared. Substituting in 1, you'll get that. And if we substitute in 0, we're going to get minus, this is going to be 0, and this is just going to be, this will be 1, so minus a half. So that's our answer there. Now, e squared minus a half e squared is a half e squared, so it's half e squared minus 1 on 2. Again, I really like volumes of revolution because I think it's so fascinating that a shape as obscure as this can have an area that's so distinct, and like it's not a bunch of decimals, we can actually approximate it to something. Okay, last question. These are one of my favourite types of questions. We're rotating the region formed between 0, 0, HR, and x is h about the x-axis. So between that, well, the point HR and x is h, which is that there, and we're rotating about the x-axis. So we're going to get a cone-looking shape. Now we might want to find the equation of that line. The gradient is going to be minus r on h, so r minus 0 and h minus 0, and the y-intercept is 0. So therefore the line, don't know why I wrote minus because it's going up, r minus 0 and h minus 0 is r on h. So the equation is y is r on h x. Now we're rotating about the x-axis, so we need to find y squared. Y squared is r squared on h squared x squared. And we're finding the volume, which is pi times by the integral from 0 to, we're integrating to h, because we're told it's between 0, 0, hr, and x is h. So we're rotating to h, because that's our limit there at x is h. So from 0 to h of r squared on h squared x squared dx. Now r squared h squared, that's just a constant, so let's bring that out. R squared on h squared, integral from 0 to h of x squared dx, which is equal to pi r squared on h squared times by h cubed on 3 from 0 to h, which is equal to pi r squared on h squared times by h cubed on 3 minus 0, because 0 cubed is 0. We cancel that, and we actually get 1/3 pi r squared h. And we're done. Thank you.